Hello, everyone. Welcome to the IEEE Communication Society podcast number 11. And today we are fortunate enough to have Professor Ana Garcia Armada from Universidad Carlos III de Madrid in Spain, if I said it right. And we'll be talking about several of the aspects around 6G and some technologies that will actually make 6G a reality, and some research areas and some research topics that are going around these 6G objectives that we have. So first of all, welcome, Anna. Thank you so much for joining us today. So maybe we can start our conversation with something more, sort of overview of what has been happening in sort of 6G objectives that we have. So we recently have this IMT 2030, slash 6G framework, where we have, new enhanced capabilities around integrating sensing and communications, having integrated AI and communication, and also trying to provide ubiquitous connectivity. So we are moving, beyond that triangular framework that we have had earlier. Now we are with this hexagonal framework. So I wanted to ask your opinion on what do you think, about this importance of these technologies and, where we are heading with all these objectives that we have created with our 6G framework. If you would like to touch something on that, please.
Sure. Hello, Aryan. Hello, everybody. And it's a real pleasure. We are in this time that happens once every 10 years that we are fortunate enough to be able to define what the new generation of communications is going to be, in this case, the 6G. And of course, the first thing is to wonder or to ask ourselves what it is for, why we need a new generation, what is the vision. And then once we know what we want to do that cannot be achieved with 5G, then we will come up with new technologies, right? So the ITU already has a vision, and I think the whole community of researchers and industry has a vision. And essentially, I think the most important features of 6G that we cannot do with 5G are this seamless connection of the real, physical, and the digital world.
Right.
And this, of course, needs a lot of intelligence. So AI must be native in these new technologies. But it needs also to be able to navigate in our real and digital world in a way that we don't notice what is real and what is not. This needs a lot of sensing. And so that's why integrated sensing and communications is probably one of the most important technologies, I think, for 6G, and one that we are not able to do today, by no means, with 5G.
Right. So we see that we have these enhanced capabilities over our current infrastructure that we have had. So we have massive connectivity. We wanted to achieve low latency communication and, hyper reliability solutions and so on. So what do you think about the sort of research that your group is working around? Are they sort of aligned with these 6G objectives? And if they are, so what kind of progress you have made with your group towards these sort of 6G solutions that we are talking about?
We work essentially in the physical layer. So all the main requirements of 6G have a big impact on how we design our waveforms, our transmitter and receiver algorithms.
Yep.
We focus a lot on some KPIs of 6G that were not possible yet with 5G. For example, the high speed, high velocity of movement, right? For 6G, the plan, or at least the wish of the ITU, is that we can communicate on the move when the movement is up to 1,000 kilometers per hour,
right,
which is really high,
very
right?
high, yeah.
I guess they are thinking also on satellites, LEOs, or, And this has a huge impact on how you design the waveform, because in the past, we always somehow postponed the problem of the mobility. So at the beginning of OFDM, OFDM started for broadcast and for wireless LAN, and then there was no movement or very low movement, right? And then eventually it came to cellular, but still, high mobility was never a problem that was like in the agenda, and it's not solved. And now we really need to solve it. So we're thinking of modifications to OFDM, because it is true that OFDM is the waveform that everybody likes, and it is the preferred one for operators and manufacturers, because not only because it solved the multipath problem, but because now, with the structure of OFDM, putting the data in the time and frequency grid, it's a very powerful way to schedule a lot of users. And this is something we don't want to give up, right? So we are trying to make modifications to OFDM in a way that we don't substantially change its nature, but we make it robust to the peak to average power problem. That is also an important problem because we want to extend coverage and we want to go to higher frequencies, and amplification is a problem, and to high-speed movement.
And this waveform design issues, I think I also see in ISAC, it becomes very important for integrating sensing and communications together. So generally, I mean, people are coming with OFDM solutions, OTFS-based solutions. So what are your thoughts on that? I mean, if your group is working around these areas of waveform design in ISA, because it's an important aspect, because you are, doing multifunctionality, like two operations together. So to really come up with the good coherence between these operations, you require a good waveform, an efficient waveform. It has to be cost efficient as well. So do you have any thoughts around these aspects?
Yeah, actually, the sensing or the localization is extremely related to the channel estimation. And in the past, we have always been estimating the channel to do the coherent demodulation or to do the beamforming, but never really thought of it as a source of information. It was just a means to get to the final communications target. But actually, there are a lot of people and ideas of how to really exploit all this channel state information to get information of the environment. And this can be done with OFDM. And actually, there are a lot of works using Wi-Fi to see beyond the walls. And I mean, it's quite amazing, right? But it is true that OTFS brought us the idea of going to a new domain where you put your information and maybe also your pilot reference signals in the delay Doppler. And this is very interesting because this is very, very closely related to how you sense the environment, because at the end, the delays are telling you the distance of the targets, and the Doppler is telling you the speed, the velocity. So it is getting the way we communicate closer to the way radar or localization work. And this is extremely interesting. I'm not sure at the end OTFS is going to be the preferred waveform because maybe it has some complexity. It's maybe not so clear yet how to do the multiple access or multiplexing of many users. But it is true that it brought this idea of working in the delay Doppler. And many other waveforms came, modifications of OTFS, OFDM, or well, there are so many, right?
Yeah, several variants.
And even probably with OFDM, still, if we think of how to design the reference sequences, we can do this work processing in the delay Doppler. So I think this is very exciting because we are in this time of every 10 years where we need to think what is the physical layer, what is the waveform we are going to do.
I mean, hand in hand, both research and development work is going on. I mean, first you sort of imagine, you kind of dream about the technologies and what kind of things theoretically on paper, how they can work. And then, you try them around on your test beds or your prototypes and so on. So I do see that, even many industry stakeholders are taking part into kind of testing and validating these ideas that we have in theory.
This is very important because, we need to make sure the assumptions, sometimes you do simulations and maybe, the channel model is not realistic enough.
You do some assumptions.
And you need to, at the end, test what is happening. And this is very important for all these new things that we want to see, like the ISAC, or the non-terrestrial networks that we want them to be completely integrated with the terrestrial, and that has an impact on the waveform again, because satellites are moving, there is again movement, there is all this long distance, so the amplification, all these problems repeat, no? And there is also the energy efficiency. I think you have worked a lot in energy efficiency aspects in non-terrestrial networks, right?
I mean, it's a very important topic. I mean, you see that earliest of our 5G-based services, I mean, at least in UK, for example, so in 2019, 2020, when we were rolling out these standards, the devices, the equipment, the services were not very energy efficient. So, I mean, we were throwing in all this massive connectivity, but we were not so, sort of convinced with, let's say, the energy efficient aspect. So cost efficiency, energy efficiency is very important. I mean, my group has worked around, for these energy efficient architectures, for NTN, for satellite-based connectivity, and also for the integrated sensing and communication as well. So how to make your system more optimized, how to select, let's say, a certain number of antennas or certain number of RF chains that you have, or to optimize really your quantization, right? So how you do your sampling. Do you really require, 10 bits or 12 bits every time? Or you can use 3 bits and you can still achieve very energy efficient solution. Our group had been also working around. So I do agree with you actually that it's a very important aspect. And this has also been included in, 3GPP release 19 sort of working groups to work around, mobility aspect, which you mentioned, to achieve like high, data rates, which has been the goal for many years now. And also to achieve, massive MIMO solutions. And, ISAC is an addition there. So you have some early study items already, decided, and industry use cases, about 32 of them are already there in 3GPP release 19, where the work is, it should be centered around. And NTN is also there, then AI and, machine learning, especially their applications to next generation RAN, radio access networks, or even ORAN, open radio access network. So, all these works are going on. So, it's good that we are talking about these sort of technologies one by one. I also wanted to ask you, just linked to that is, so we do see that we're also focusing some work around next generation MIMO in sort of 3GPP release 19, let's say. And we are always looking for these solutions to achieve these terabits per second capable speeds, but with minimum resources possible. So what do you think about, what kind of MIMO techniques or MIMO technologies that can actually, we are able to see in our, let's just 60 devices in, let's say, next few years, or, 2030, 2032 or something. So what do you think about that?
Well, MIMO has been a revolution, right?
Yeah.
And logically, we ask ourselves how to continue with this powerful technology evolving in such way. And massive MIMO was probably the logical evolution. But we today see several massive MIMO base stations, but maybe not that many. And that's maybe because of the complexity that you were mentioning, right?
Yeah.
So then cell-free massive MIMO that we don't really see today for 5G, but maybe we will see at the end of the 5G before 6G, I don't know. Cell-free looks like the logical evolution. You still do the MIMO, the massive, but not collocated, but in a more dispersed way, so it gets easier. But this was the comp, right? It happened at least in the standards. It was defined already for 4G. But I think the coordination of several base stations, the architecture of the network was not ready for that. But now, with all these centralized and distributed units and the ORAN architecture, maybe it is maybe we're approaching the moment where we really can implement these cell-free architectures. And then logically, we are already working on the ultra-large massive MIMO, right? So if you can do it very large, what can you gain? Well, theoretically, the more antennas, the more you can gain, right? But of course, it has also many complexities and new things, like if it is so large that you don't see the same scenario from each of the antennas, then the channel is not spatially stationary. You need to think of new ways of processing. And this is very, very interesting and very challenging. You can use it for communications and for sensing and positioning. We have a new project now, a European project that started. It is actually a doctoral network with a lot of players in Europe. We have Ericsson, Nokia, Vodafone, and many universities, specifically working with 15 new doctoral candidates on the challenges of ultra-large massive MIMO for communications and for positioning. Well, in a few years, we hope to have many new techniques and solutions in this.
Nice.
In this regard.
We need to work around these sort of ideas where we can utilize as low possible as of the resources and achieve the highest capacity or highest energy efficiency possible. So I also think that in these sort of ideas, spectrum will also play a big role, because you need to come up with, I don't know, spectrum reuse or any sort of spectrum solutions that we need to utilize. So I remember you and I have recently done a paper as well on utilizing centimeter wave and sub-terahertz. This is out there online. With many of our collaborators we have worked around. So we do talk about some of these aspects as well, that how we can use, let's say, low to mid-band spectrum, and also perhaps in some geographical locations we may even require high frequency bands like sub-terahertz, or I mean, it doesn't even stop us from exploring even higher bands, terahertz. I mean, if you are talking about massive MIMO systems and trying to explore very high data rate, ultra high data rate sort of aspects. So I think we should look into the spectrum aspect of it as well. Don't you think about that?
Yeah, and centimeter waves, I think, are a very, very good solution, because, millimeter waves, terahertz, we, of course, need to explore that, but they are probably very challenging. And having millimeter waves in 5G has been a big challenge.
Yeah.
And it is not completely solved yet. So if we can go to frequencies that are a little bit less high, but still, with plenty of spectrum availability, the closer we get to the 6 gigahertz, the better. And I think these are going to be much easier to deploy and closer to the understanding we have today, but still with challenges that get us closer to the higher frequencies, but in a soft way, without a very difficult
That's
step.
the idea. We don't want to change too much into our 5G infrastructure that we already have with us. I mean, we want to stick to 7, 8, 10 gigahertz frequencies, 12 gigahertz. I mean, if you go quite close to millimeter wave, you have blockage effects, path loss effects. Your signal gets distorted, I mean, with some sort of disturbance that you may have. So I think it's very good that you raise this point. I also wanted to ask your thoughts on some sort of future prospects of these technologies. I know that we have this consensus with us, with the community, to work around, integrated sensing and communication, AI communication, NTNs, and all these technologies we're talking about. But what do you think, that is this something that we are aiming for only, let's say, immediate future? So let's say about 2030, and then we have these things in our devices. You have like a mini sensor sort of thing in your mobile phone. It is able to do both, environmental monitoring and also at the same time communicating as well. Do you think that this is more like an immediate future that we see, or this is very sustainable, that we see that maybe in 2040 you are still trying to mature these same technologies, or you will come up with something new like quantum or something, something else? So what do you think about the future prospects?
Most likely, we will be still working on the same technologies for a long time. Like it happened with 5G, there were many ideas, requirements, visions for 5G that we were not able to accomplish in such a short time, and now they became goals for 6G to be perfectioned. And this will happen for sure in the future. I mean, quantum is amazing, but I think quantum will need much longer time. And meanwhile, we'll still have a lot to do with maybe more classical communications and sensing, with the great help of artificial intelligence that is now aiding us to solve problems that we didn't know how to solve in the past. And I think all this has a long way to go and to be perfection before we get to things that are completely, breaking our rules and doing things in a completely different way.
I mean, I like that about 6G. What we're aimed is beyond connectivity, beyond just communications. I mean, we are implementing AI, cloud native solutions, as you mentioned, and many other sort of technologies. But these are beyond communication. You're not just trying to achieve communication. You're trying to sense. You try to localize. You're trying to do some imaging, maybe some 3D localization that we are doing, positioning, or you're trying to use different, I don't know, applications like smart healthcare or robotics, for example. 6G you want to use for robotics. I mean, so it does look like that you want multifold sort of benefits that you want to achieve with 6G coming into picture.
Yeah, I think this is a matter of efficiency first, and also a matter of having more possibilities, even for for the industry in our field, to have better products that they can market, of course. This is also an important, I think, an important reason to go to more. But efficiency, I think, is very important.
It is very important, right? I mean, just before we conclude, so I also have one sort of announcement to make. I know you also work on sort of liquid antenna arrays and the sort of reconfigurable nature of the transmission. So we'll touch that topic perhaps in a later podcast. But I wanted to mention that recently we have the ETI as well, the ComSoc Emerging Technology Initiative on electromagnetic signal and information theory that has been approved very recently, and that will roll out many activities in this area. I mean, the areas of reconfigurable antennas, meta surfaces, or intelligent transmission, dynamic transmission, whatever you want to call it. So we are fortunate enough to chair, together with many other colleagues as well in the team. So we have close to 100 people who are like the founding members and governing body members and so on. So we look forward, I mean, from our colleagues as well to take part into that emerging technology initiative that we have recently, that has been approved recently. So with this, thank you so much, Ana, for joining us today in London. And it was really great to chat with you. And I hope that we meet next time in a different podcast, talking about more things, more detailed things, in fact. But thank you so much for joining us today. Thank you so much.
With pleasure. Thank you.